Okay, so now let's give a geometrical interpretation for quantum states. So here's where we were. So we are thinking about the state of an electron in a hydrogen atom. So its energy levels are quantized: ground state, first excited, second excited state, etc. And of course, if this was a classical system, we could use it to store some information. You know, if there are three possibilities, then it would be a trait of information, 0, 1, or 2. And okay, so now in general, the state of this system, as we saw, is a linear superposition. If it's a k-level system, then the state of the system is given by a linear superposition: alpha 0, 0 plus alpha 1, 1 plus alpha k minus 1, k minus 1. Meaning that it's in the ground state with amplitude alpha 0, etc., etc. Now there's a different way we could have written the state of the system. We could have just, if we have to write out k different complex numbers, one way we could do that is by writing it down as a k-dimensional vector. So we could have instead written it by putting these k numbers, stacking them up like this. And so these are really two equivalent ways of writing the state of the system. But if we write it out as a vector, then of course we can also, you know, we have a picture of it. So for example, if we had k equal to 3, then the way we could represent the state is by representing it as a unit vector. It's a unit vector because the sum of the squares of these amplitudes is 1. So we'd be representing it in three-dimensional space if k is equal to 3. And if this is the x, y, and z axis, then our state vector would actually be a unit vector in this space, and we could label it, you know, it would be this vector, right? And it would be a unit vector. It would be sitting on a unit ball like this. Sorry with my drawing, but it's a unit ball because of course alpha naught squared plus alpha 1 squared plus alpha 2 squared equal to 1. So it sits on the unit ball. So now we could ask, what are these three basis directions? What does the x-axis represent and what does the y-axis represent? Because these are also unit vectors. And so of course this x-axis represents, this is 1, 0, 0. Which means alpha 0 is 1 and alpha 1 and alpha 2 are 0, which means that the system is in the state 0, the ground state. What about the y-axis? Well, it's 0, 1, 0, right? And that corresponds to the state 1. And the z-axis, which is 0, 0, 1, it corresponds to the state 2. So here's the interesting thing to think about. So the fact is that this funny notation we had where we thought of the ground state as, you know, we wrote it as 0 inside these funny brackets and the first excited states as 1 in this funny bracket. It's just another notation for a vector. Except that, you know, usually when you write down a vector in usual vector notation, you write it as a vector u, and you put this little bar on top. Here what we are doing is we are directly saying that the ground state represents, it's the 0 state for us. And so we write the label inside these funny brackets, and that's our notation. This is called the Dirac notation, invented by the great physicist Dirac. Okay, so that's one way to interpret a quantum state. A quantum state of a k-level system is just a unit vector in a k-dimensional complex Hilbert space. So it sits inside C to the k. Okay, so now, of course, if we had a qubit, so we're sitting inside a two-dimensional complex Hilbert space. And if we were to write the state of the system, if we were to say that it's represented by the vector psi, well, the way we represent it is psi inside these funny brackets is alpha 0, 0 plus alpha 1, 1. And now if alpha 0 and alpha 1 are real, I can actually draw it. Okay. This is the 0 state, that's the 1 state, and that's our state psi. It's a unit vector, so it sits on the unit circle. And now we can ask, well, what's alpha 0? Well, alpha 0 is this intercept. It's the x-intercept, and alpha 1 is this y-intercept. And now if you do a measurement, if you make a measurement, the probability that you see that the outcome is 0 is alpha 0 squared. Well, in this case, I'm saying it's real, so it's just alpha 0 squared. And the probability you see 1 is alpha 1 squared. And of course, the new state in this case is just 0. In this case, it's 1. So here's another interpretation of the measurement process. So when you do a measurement, so if you think of this angle as theta, and what happens is that the probability that the outcome is 0 is cosine squared theta. It's the cosine squared of the angle between psi and the 0 axis. And similarly, the probability you see a 1, well, this is really pi by 2 minus theta. And so it's cosine squared pi by 2 minus theta, which is sine squared theta. So measurement is this process where the state vector is projected either onto the 0 state or the 1 state. And the probability it's projected onto the 0 state is just cosine squared theta. And 1 state is cosine squared of the angle that the state vector makes with the 1 state.